Good afternoon, everyone. Welcome to the weekly Tuesday car seminar, which today occurs on Monday, just to show you that we can be flexible. We have two seminars today, right?
Yeah.
Who is giving the seminar?
No, but it's just one device.
It's the
Yeah.
two of you device.
Yes.
Okay, good. So we have, I'll give a little bit of background, but a number of years ago, we received funding from the Federal Transit Administration, which is the agency of the U.S. Department of Transportation that governs public transit in the United States. And every transit agency in the U.S. receives some kind of financial support from the federal government through the FTA. And in particular, the FTA cost shares the purchase of buses with transit agencies. A number of years ago, many, this is not new, the FTA started a program called Low Emissions, No Emissions Transit Buses, low, no. And as part of this program, the focus was, can we have in urban areas where typically transit buses operate, can we have vehicles with low or no emissions? And obviously, battery electric buses and hydrogen fuel cell buses are the most obvious alternatives. So we started doing work years ago on battery electric buses, and these things have evolved over time. We've been working on it for quite some time. So today, Luca and Ani will give a two-part seminar to explain various aspects of the work we do. Is that a good introduction?
Oh, perfect.
Okay.
Thank you. That was a really
Then I'll turn it over to the
introduction. Yeah. So, talking about transit buses, as Dr. Insoni has mentioned, let's say that battery electric vehicles are a really good fit. And this is particularly because of their type of driving patterns with a lot of start and stop, which allows for regenerate a good amount of energy. However, the main problem of battery electric vehicles is having a good, accurate estimate of their state of health. So this is dependent on several factors, such as driving behavior, weather conditions, and in particular, if you have extreme weather conditions such as really cold or really warm environments, this is really detrimental for the battery pack. Then charging habits, roughly speaking, the faster you charge, the worse it is for you for the health of your battery pack. And finally, also the patterns. In particular, recent studies have demonstrated that long resting time of parking can be beneficial for the battery state of health. So transit agencies need to deal with all these aspects when they are looking into battery electric buses. And so in the end, what happens to them is that when they purchase the same battery electric bus, this can behave completely different depending on where to deploy it and the climate condition and the driver behavior. And on top of that, transit agencies need to deal with the lack of operational feedback because they don't have tools that allow them to track the battery health over the life of the buses. Then they have limited testing practices, and in particular, let's say that the current programs are lab-based, and as you can imagine, lab-based testing is really far from what people's experience in real life. And finally, let's say big burden for transit agencies the cost, because battery electric buses are pretty expensive, and around 1/4 of the price is in their battery. So when they need to replace it, if they don't, it's not under warranty, it's a big deal. So, having given this brief introduction, the main goal of the project in which Annie and I and other people have been working over last year is to develop a software tool that can allow fleet operators, on the one hand, to do data analytics. So our aim is to deeply analyze the real-world data to gather insights and also to provide feedback and suggestions to transit agencies. On the other hand, what we are trying to do is to monitor battery state of health. And this it can allow transit agency to improve operation efficiency by enabling better decisions with fleet management, can allow to have better reliability because this can allow to enable guidance in the maintenance strategy. And finally, as you can imagine, which is really important for transit agency, allowing cost savings. So here you can see the workflow of the presentation that we are going to give today. I will firstly focus on the experimental investigation of the data that we have access to. Then I will focus on the model, the digital twin that we have been developing so far, the validation of the digital twin against the experimental data, and finally, Annie will describe more in detail the web app on which we have been working and we are still working on. So looking at experimental data, in this work, I would focus on the data that COTA shared with us. COTA, the Central Ohio Transit Agency, the transit agency that serves the area around us. And they have 50 battery electric buses in their fleet. They have been started to be used from October 2021. And we are showing in this presentation data until October 2025. This data is, let's say, connected to a proprietary cloud and is transmitted to the proprietary cloud continuously. And in this plot, you can see the cumulative distance of the fleet as a function of month and year. And as you can see from the start deployment of battery electric buses until, let's say, 2023, COTA didn't use so much battery electric buses, but they started using more intensively starting from January 24 until, let's say, October 2025, which is where this data set ends. In their fleet, they have all the BEVs that have the same specifications, and in particular, they are nuclear C40, which is a symbol of for the Americans 45, for the Europeans 12 meters, and has a cargo weight of around 15 tons. And here you can have some details of the powertrain, and in particular, you can see how the high voltage battery feeds some low voltage loads through a DC-DC converter. And then there are some high voltage loads, in particular on the compressor, the PTMS, HVAC, and the air compressor through an AC-DC converter. The only component instead that, let's say, is directly fed to the actual high voltage battery is the electric heater, which works at a voltage that is similar to the voltage battery. And here you can see that the electric machine has a maximum power of around 160 kilowatt, and this is alimented by an MC battery pack of around 525 kilowatt hour. So in this slide, I'm showing you the data post-processing that we follow it for the experimental data. So first of all, we use API call to source the data that are stored in the proprietary cloud. At this point, since there are some period of time in which these buses are not used, for example, there could be faults or whatever reason for which these buses stay mass in the depot, we divide it in active and inactive sessions. Then looking into the active sessions, we use geofences in order to divide in driving and charging sections. And then once we had a driving section, which will define as a shift, we were able to divide it in segments. And in particular, as you can see here, the segments are the deadhead from the terminal to from the depot to the terminal. Then you have the layovers at the two terminals and the actual service route, which is the connection between the two layovers. So at this point, I want to give you some additional details so you can further understand this procedure. For example, here you have in blue all the, it should be blue, sorry for my computer was a better blue. So you have all the operations of the battery electric bus in this plot as sequential latitude and longitude. And you can see how the points that correspond to the depots, which are Field and McKinley, are highlighted. And then in this additional slide, you see the data divided in driving and charging sections. And in particular, you can see that for each driving section, there are the shift, each shift with a different color. Here, if you are familiar with photo routes like Annie, you can actually I understand, visualize which routes are. I'm not able to. And in the end, instead, here you have all the charging sections, and they are, as you can imagine, all in correspondence of the two depots, McKill and Fields. In this additional slide, instead, I wanted to show you how, like, I'm visualizing how the shift is divided in segments. And in particular, one, you have the driving shift, how we divide in layover, service routes, and deadheads. And the two plots basically represent the same information. On the right is two-dimensional, so you only see latitude and longitude. All the routes are overlapped one over the other, while on the plot on the left, you have a three-dimensional plot with the expansion on the time dimension on the z-axis. And basically, what you can see is that the deadhead connects the depot to the terminal. And then at this point, you have the service routes that are basically like over the same coordinates, as you can see from the plot on the right, because they are all overlapped. And then the layovers always in the same point. So once we were able to gather this high level of detail, what we did was targeting the first inbound route and the first outbound route for each ship. Okay, can you hear me? Yes, okay, fine. But yeah, oh great. Sorry. So we were having, as Dr. Rizzoni was saying, issues with talking about state of health of batteries with the battery of the microphone. So I took my computer and at least this can work somehow.
Do you want to share?
No, we can use
It's not sharing.
Oh, it's not sharing anymore?
And we signed out of this.
In case I can share here.
Yeah, it's not even clicking.
Well, it's up there now.
Oh,
It's sharing now.
that's
Oh,
great too.
great. Okay.
I think it was having a moment.
I think so.
Oh,
And then, yep.
oh, nice.
And then turn the camera
So also the camera. Where is it?
here on the left. Go a little left. Oh,
Oh,
yep.
Yeah, select that.
okay.
Camera.
Yes.
There you
Okay. So, okay, perfect. So just for confirmation, everybody hear me and you can see, right, the screen? Okay, perfect. So, where we were, okay, here. So basically, my comment before was that, as I was saying, ambient temperature experience seasonality, but the most interesting aspect to look into this plot is battery temperature, because even if you can see that it experiences some seasonality, in fact, you can see here some variations. In general, the variation of temperature is much more constrained. And this is thanks to the BTMS that is in charge of keeping the battery temperature inside a safe range. And this can also be seen from the plot on the right, where basically you have that the battery temperature has a peak around 25 degrees, and then you have a steep decrease at higher and lower values. Then
Luca,
yeah,
share your laptop.
it's better if I share from a laptop. Sure.
Not sharing.
Okay.
But the audio works. Yeah, the audio says it works.
Okay.
Just share from the laptop. And then. Okay.
Wow. Yeah.
Hold on. We need to change this.
So,
On. Oh.
so I don't know, like Meg, you can see, and you can. Oh, okay, perfect. So we do from my computer.
Thank
Nice.
you, Meg.
Yeah. We will extend a little bit.
We
Or
do what we can.
I will try to be faster. Okay, so going on, I wanted to, let's say, focus in this plot where we have we can analyze the aggregating matrix, and in particular here you can see in the plot on the top the specific energy as a function of temperature, while the top on the plot on bottom the auxiliary power consumption as a function of temperature. And as expected, the auxiliary are highly dependent on temperature, and they also affect the bus energy consumption. In fact, especially you see the increase with lower temperature. There are other factors that play a role in the increase of energy consumption with temperature, that are rolling resistance, drag, but let's say that the major player is the increase of the auxiliary power consumption. From the plot on the right, we can give more granularity in auxiliary power consumption, and in particular they are divided in high voltage, low voltage, and heater. As you can see, the low voltage ones are the ones that are less affected by temperature, and this is because in the low voltage, you have many auxiliaries such as door opening, lightings that need to operate whatever temperature is outside, and so only the efficiency is affected by them. Instead, in high voltage, you have the compressor, for example, BTMS and HVAC, which are operated to cool both the cabin and the battery pack. And instead, at low temperature, you can see that the heater is the one that is the bigger player, and in particular is linearly dependent with temperature. Some particular additional analysis can be done on regenerative braking because, as I was mentioning before, for battery electric buses, regenerative braking can play a big role. And in this plot, you can see on top the specific regenerated energy, while on bottom the share. So regenerated energy divided by the energy discharged by the battery. Again, here each point represents a trip. And as you can see, there is a clear dependency with speed. And this is, let's say, clear because the higher the average speed in a trip, it means the less opportunities you have of braking, and so having start and stop patterns, and so the less energy that you can regenerate. But then on the other hand, if you want to see, like in the share, you see less dependency because with higher speed, you also improve the energy efficiency of the vehicle. So in the end, you have less regenerated energy, but also less battery energy discharge from the battery. In this plot on the right, you have the same variables, so specific regenerated energy and share, but plotted as a function of temperature. And it's really evident the dependency on temperature. And as you can see, of course, like with lower temperature, you have, of course, that the battery also becomes colder. And a colder battery temperature, like colder temperature for battery means also higher resistance, and then so it means higher losses. And so in the end, you have that the maximum energy that you can regenerate decreases. Instead, if you look at the share, this effect is even more evident. And this is because at lower temperature, you not only have less energy regenerated, but you also have higher energy discharge from the battery. And so this is detrimental for the share. But something that is evident from this slide is that the share are pretty high because it's between 20 and 50%, which is a remarkable value. So having done, let's say, some investigation of some of the aggregated metrics that we computed, I want to focus a little bit on the digital twin development. And in particular, our goal here was, once we developed a good understanding of the operations of the real world battery electric buses, we wanted to convert our knowledge so that we could obtain a digital twin on which we could virtualize all the operations. And basically, the goal of the digital twin is that somehow we want to close the loop, and through the simulations, we can obtain some insights that can be used in the real world. So the first step was virtualizing, digitizing the COTA routes. And we did it by first obtaining the stop locations from publicly available records. Then at this point, we converted coordinates in network edges for simulation in Sumo. Then we also added information about traffic light location, stop location, speed limits, road grade. And on top of that, we also sourced information about climate conditions. We sourced data from 2021 to 2025 to match the experimental data. Then we developed a high fidelity simulator, and in particular, apart from the route and weather information that I mentioned before, we also developed a high fidelity simulator that incorporates vehicle dynamics and load transfer. And this is particularly important for estimating have a good estimate of the energy regenerated through regenerative braking. We added an enhanced driver model because we wanted to obtain realistic behaviors of different types of drivers. We included the possibility of having a passenger load capacity, in particular with passengers entering and exiting the bus at each bus stops. And finally, we spent quite a good amount of time in modeling the auxiliaries, since, as you have seen in the previous slide, auxiliary have a huge impact on the bus energy consumption. Then we developed a computational framework so that we could explain to Ohio Supercomputer Center in order to run case simulations in a reasonable amount of time. And we did it by using the information that we had from the cutter routes and then integrating the weather history and the route info that I showed you before. And then we introduced the possibility to have several different initial conditions in terms of date and time, initial battery SOC, and driver behavior. All these information are combined in a matrix, and then there are several simulations that can run in parallel on multiple workers. And then, as you can imagine, for each simulation, we have detailed models that I was showing you before: driver, load load, road load, powertrain. And each simulation provides detailed results. Here you can see the route with all the stops and the stops taken. On this plot on the right, you can see the speed of the bus as a function of distance and the variation of passengers as a function of distance. And then what we did was writing some code to basically process the simulation data, similarly to what we did with the experimental data, to obtain some aggregated metrics. And in the end, all these aggregated metrics go to a unified database. So at this point, we could have similar results from the experimental side and the simulation side that we could compare. So looking at, for example, some specific simulation, it's really interesting to, let's say, have a better look at the energy flows. And in particular, this Shanker diagram shows how the energy goes in the battery electric bus. And as you can see, the energy that is discharged from the battery is mainly used by the electric machine for propulsion. And then most of it goes to the wheels. And here you have a fraction of it that is used by the auxiliaries, which is not negligible. And then you have some losses at inverter, electric machine, and drivetrain level. Then some of the energy is used for road load. So it means it's lost in the road load. And then, as you can see, a good amount of it can be regenerated through regenerative braking. And then, as you see with this flow, some of it is lost in the drivetrain, the opposite flow. And then this, let's say, side that you see here, this ratio is basically the energy that can be sourced again into the battery. And so when before I was talking about share, it was basically this value divided by the total energy discharged from the battery. And as you can see from this plot, regenerative braking play a good, important role here because allows to drastically reduce the energy that is used from the grid. Here you have some additional detail on the total braking energy. And here is just to tell you that when you brake, most of it comes from the electric machine through regenerative braking, and some is lost in the drivetrain, whilst some energy is lost in the mechanical brakes. So I try to fast a little bit up since we had some problems. So my final part will be the model validation. And here, as I was telling you before, our goal was to compare the aggregated metrics from the experimental side and the simulation side. So this plot is basically a post-processing of the results. And here you have all the experimental and the simulation trips, and they are grouped in bins that are centered in the values that you see below. And then for each bin, apart from plotting all the plots, we computed the box plot. And so in this way, you can have an idea of how our model in terms of large-scale simulations is able to replicate real-world results. And as you can see, the auxiliary are really well calibrated because we follow really well the experimental values, both in terms of median values and also in terms of probability distribution. Then this plot on the right just gives the probability distribution of the average vehicle speed. As you can see even here, the model matches really well experimental data. And in this slide, we do a similar analysis, but on the battery and that net energy consumption. And as you can see even here, the model is able to replicate really well the experimental data. And on the right, you have the same information, so the specific energy consumption, but plotted as a function of speed. Here, the model again replicates really well the experimental data. We need to calibrate a little bit better for really low values of like vehicle speed and really high values. So basically those trips that are or only urban or only highway, but we are working on that. Here, some focus on the regenerative energy. And as you can see, we spent some effort in calibrating the model, and we are able to match really well the experimental data and also to follow, let's say, the degradation, like the decrease that you have in the possibility of regenerating at lower speed. And here again, you have the same information, but plotted as a function of vehicle speed. And the same comments that I did before apply even here, because the model captures really well, let's say exceptionally well at average speed, and must be improved slightly at high and low speed. One final analysis that can be interesting for this presentation is driver aggressiveness. And in particular, in our large-scale simulation, we simulated different types of driver that can be clustered in 3 groups that are calm, normal, and aggressive. And here you see the 3 types that are represented in green, yellow, and red. And basically, as you can see from this plot, driver aggressiveness does play a role in the energy consumption. And by looking at this enlarged area, you can see that passing from calm to aggressive can, let's say, cause an increase of the energy consumption of about 10%. But something that is really interesting is that if we focus not on the net energy consumption, but on the energy discharged from the battery, you can see that the box plots are more distanced. So basically, passing from calm to aggressive causes much more energy discharge from the battery. But on the other hand, it also allows for higher regeneration. So driving aggressively on the one hand, this causes a more energy discharge from the battery, but on the other hand, allows for regeneration. Here, I'm not saying to drive aggressively, but in the end, as you can see, the main outcome is that, let's say, the discharge energy plays a major role. So overall, the net energy consumption increases. So this is, let's say, the end of my part. So now I will leave the floor to Annie, which will talk about the web app application.
Thank you.
Thank you, Luca. Do you take questions?
In the end.
In the end. Yeah. So as Luca mentioned, a goal of this project is to develop a web application that we would then deploy to transit agencies nationwide. As you can imagine, transit agencies operate differently in terms of conditions, routes, charging behavior, number of passengers. Everything is different. So our goal is to take what we've learned from our digital twin development and what we've seen from experimental data and combine them into a smart monitoring tool that we can then give to transit agencies to make more well-informed decisions about the health of their fleet, new best practices, and also extend the life of their batteries. So web application development can be split generally into 3 distinct parts. One is front-end development, which is what does the user see and what can the user do? The second is back-end development, which handles data ingestion and also asks and needs from the front end and helps communicate with the database. The database, of course, stores data in a way that we can predetermine. So we'll go through each piece. We'll start with the backend, primarily to discuss our data ingestion process. So as it stands right now, the web application uses data generated from the digital twin. So currently, we accept data and we process it and clean it, which means we remove rows that don't have values or have null values just for the sake of data clarity. And then we aggregate them into weekly aggregates, which are then fed into a model that we've implemented into the application to perform a simple state of health estimation, state of health decrease. And that data, along with the aggregates, are both stored in the database. So the backend also can determine when data is fetched, how data is processed, and we primarily keep the data weekly aggregates for each bus in each fleet. Next, to discuss the database creation, there's 2 big things at play. The first one is what we like to call a permanent database, which keeps our weekly aggregates per bus, per fleet. The next, we've devised sort of a cache to have more granular data from a more recent period of time, let's say from the last week, that can answer more on-demand questions from transit operators. So the way that these two are formed are what we outlined previously with backend development, in which we accept data, we compute our aggregates, we compute an SOH estimation, and all of those are stored in the permanent as well as the cache. The second part of this is, what does the user see? So the user wants to visualize data, both aggregates and more recent granular data. And we've also coined something called a report, which is something that an operator can use to say, from this period of time, I want to see driving data from this vehicle or for the entire fleet. And I want to see energies, battery temperature, things that are either aggregates or more granular information. Now, what if a transit operator wants to see data that's not from within the last week? What if they're working on scheduling and they want to see something from a previous block of time? Then we introduce something or a worker that can fetch a specific day for, again, one or more buses, that performs the same type of data processing, but also presents this in a more granular way, such that a user can visualize and generate similar reports. So what we need to move on to next, as I mentioned previously, the application is built on aggregates from the data from the digital twin, is we need to extend this to transit agencies and real data that we would get from them. So what's important to us is we want to make sure that we can say or have information for driving segments, parking, and charging. So for now, we've developed an initial pipeline that first accepts data from transit agencies, chunks them into driving, or right now, in service and out of service, and then groups them by weeks and computes weekly aggregates, just as we did before. Lastly, in order to make this more extendable to transit agencies across the country, we need to make this cloud hosted, which essentially means we put our front end back in a database on external servers such that things are more secure, scalable, and all the computational load of data queries and data post-processing can be spread over multiple servers. In this way, transit operators can simply go to a link, log in with their credentials, and access their data. Lastly, we want to go over the front end. So what has been developed from last semester and this semester. So for that, we've constructed a brief demonstration in which we can go through this. Great. So right now we have login functionality. So I don't know if it's visible, but this is a .osu.edu username and password. So upon logging in, fleets would be able to see, or operators would be able to see information about their fleet, driving, charging, parking times, monthly distance, and they could change the years on this. We've also introduced time utilization, which shows how the time is spent for each vehicle for driving, charging, and parking. We've also wanted to visualize battery temperature versus ambient conditions. We also have a bus comparison table, just in general, to see how each bus is being used, as well as the latest state of health estimate. And lastly, here we have a reports widget, which, as mentioned previously, you can select a period of time. You can select weekly, monthly, or yearly, as the app stands right now. And you can visualize state of health at the beginning of the time, end of the time, distance, energy consumption, and time distribution. Lastly, we have an energy consumption plot that's also based on temperature. Now you'll see on the side, we also have a buses tab that, let's say you want to see more granular information. So for each bus, we would provide operators with the ability to see daily more information and also change the date here. There's also a search option for fleets that are very large. You can narrow down which bus you'd like to see, and a reports tab, which is a little bit more per bus and gets you the most recent data. So as you can see, the previous week has no data, so there's nothing to display, but this would provide the ability to have more recent information and customize this. In addition to this, we've also implemented login securities. So username and passwords are encrypted in a database. There's a forget password option where an email will actually be sent to you to reset your password. And we're currently working on moving forward with our real world data integration to also make sure that things are coherent. As we add more agencies, we need to ensure that the world doesn't need to change in order to add new agencies. So with that, we'd like to acknowledge all those who contributed to this project. And we are open to questions.
Thank you. People leaving time for questions.
Yeah, we try to compress a little bit.
So maybe I'll.
Yeah.
I do have a question.
Sure.
Many questions actually, but first of all, impressive work. It's super cool to see actually the app and the video and demonstration. But well, my questions are more on the other part on the part.
I came here so people can
Yeah.
hear me from home.
You mentioned several times the calibration of your model, but what do you exactly mean by that? Like,
Let's say that there's basically physical model, like physical based model. So we have a lot of physical based components. Auxiliary load, for example, are duty based cycle. So you have some duty that, and we looked at real world power absorption, and based on that, we calibrated the values, and then we adjusted it. Or for example, also the road load, like I can give you some details. Wait. So here, this is like, it was an old schematic of the powertrain, but give you an idea. But also, like, for example, the road load is all physics based, so we needed to calibrate all the factors. And so this is calibration, let's say. I don't know if I answered your question.
maybe like, is it more like a validation of your model more than a calibration? I don't know, like.
Yeah, because first there should be a calibration, and then there is the validation, because what we need to do in the end is comparing the final results with the simulated results with the experimental
But then
data.
how is like, how is this like, what is the difference, let's say, between the model and the digital twin in this sense?
So this is a good question, because our goal, we are talking about digital twin because we want to create a loop. So we want to create a virtual representation of a battery electric bus, and that must be so, let's say, like there should be so high fidelity to real world that in the end, what we want to obtain through the software tool is giving some insights to the transit agency. So in order to have that, you need to have a really high fidelity model. And so we can talk about digital twin because the model can allow to obtain some suggestion and some insights that can be used in the real world. And so in fact, the software tool, as Anthony mentioned before, is basically like sources both experimental data and simulated data. And maybe I give you an example to make it clear. You can use data analytics to do some analysis of the past. So looking at the past, you can say, oh, this is roughly energy consumption or auxiliary energy consumption, etc. But like if the model is able to replicate really well the real world behavior, you can also introduce some forecasting behavior. So through this software tool, for example, you can look in the next week and you can see the temperature forecast in the next week. And so there, if you have a really good model, and you can talk about digital twin, because then you give insights for the future, and you can, for example, if you're caught or whatever other transit agents, you can say, okay, it's better to use this battery electric bus on this route because there should be like the environmental condition should be those, and because you know which should be overall the energy consumption and the probability distribution. I don't know if you answer it. I
Like
answer it.
sort of that surrogate data analytics. So you
Yeah.
create high fidelity data that then you use to predict.
Exactly.
Yeah.
Thanks.
I don't know if you have other questions.
There are many things you can do. To give you one example, which is what transit agencies are interested in, you can use it to study different ways of optimizing your schedule.
Yes.
Because you can relatively quickly look at the benefits of assigning, if you have a mixed fleet, compressed natural gas, battery electric buses, how do you optimize which bus is best for which service?
Yeah, that's what I was thinking about, and I need to work to other people, but I have another question related if you, if no one.
Sure.
With the, most data that you have, the digital twin data,
Can you talk a little bit louder? Sorry.
were you able to gain any insight into the depth of discharge that, transit agencies are using and how that impacts, both the age and the regen capability of the buses?
So no, this is a good question for the audience. Is like if we are also looking into depth of discharge and how this affect regeneration and state of health. So we have some analysis. If you are interested, I can show you in which we were looking into depth of discharge. As I can tell you that unfortunately these buses are not that old because in the end you don't have so much aging in this utilization. So it's difficult now to say how much depth of discharge affect aging. And also one additional comment that I can say is that at one point they had some issues with these buses, so they reduced the depth of discharge. But for sure, this is something we are investigating because depth of discharge plays a big role in the aging. In terms of regeneration, let me say, if you are not really close to the highest values, which is almost never, I don't think it affects so much. This is my belief. So I don't know if I answer your question. But if you're interested, I can show you. I have some. I don't have them here, but I have some analysis I did on depth of discharge.
You want to ask your second question?
I can. This couple words on this counterintuitive driver aggressiveness result. How do you explain it? Like I like from the top of my mind, I can think if you have a more aggressive behavior, it means you accelerate more, you brake more, and I mean that involves some losses in return in terms of powertrain and like resistance in general. So how is it possible that you actually end up doing better if you're more aggressive?
No, you don't end up doing better. So being more aggressive, here you see you increase the energy discharge. So this is the energy discharge from the battery. So it's detrimental for the energy. It's in line with what you said. On the other hand, you end up doing better in regenerative braking because basically you are shifting your points and you are using more forceful braking, and this can allow more regeneration. But overall, in absolute terms, then you need to see at this plot, which is the net energy consumption. And here, as you can see, being aggressive means energy increase. In fact, like at some values it's less evident, but here there is this enlargement between 15 and 20 degrees, and you can see that driving aggressively means overall 10% roughly energy increase in the net energy consumption. So this is more in line with what you thought. Sorry, I was fast because we were running late, but this is in line with what you thought.
Any more questions?
Yeah, I don't know if there are also from.
Go here
See if there are any online.
and then unhide it.
Oh, you did it.
Yeah. And then go to the bottom. And yeah. This one. Click this. Scroll down. Nothing.
No, nothing.
Yeah.
Yes.
Yeah. There's nothing online either.
You don't have another question?
There's no other questions online at the moment,
so-
so
I think we can
I think we can,
end up here. And so thank you to everyone
and thank you all for your
for
attention
attending.
as well.
Yeah,